This is Britt Caswell with another example video. In today's video, I'm covering example 4 from section 7-1 in the SavvasRealize Algebra 2 textbook. The goal of today's video is to evaluate trigonometric ratios in special right triangles. Now, I'm going to kind of start this with a caveat of the idea that special right triangles is really important for you guys to understand as we move forward, because we're building what's called a unit circle, which relies on these special right triangles and the ratios. So if you can understand special right triangles and get the values for them very quickly using the ratios, then it's going to make your life with the unit circle a lot easier if you can't memorize your unit circle. Okay, so while this seems a little bit not as important or whatever, I really recommend making sure that you pay attention here. When I was in school, I never memorized the unit circle. I just remembered my two sets of special right triangles, and I created my values every time. But that's because I'm bad at memorizing stuff. Anyway, here we go. Now, I thought that this section was interesting in that Savvas doesn't actually use any of our known theorems for special right triangles. They just whip out the Pythagorean theorem. Which, I mean, that's fine. You could do this with the Pythagorean theorem. But special right triangles have set ratios for the sides that most geometry teachers make students memorize anyway. And so it was interesting to me that they would not just bank on those ratios already. Alrighty. So there we are. I've drawn my two special right triangles. This one is called the 45, 45, 90. And this one's a 30, 60, 90. Alright. They come from, the names come from the angles. Now, 45, 45, 90s are isosceles triangles, right? Because those two angles cause us to have two side lengths that are the same. And so if I call those side lengths x, then I plug those x into the Pythagorean theorem, which I'm way too lazy to do. You get x root 2 for your hypotenuse. So if I, for example, know what my hypotenuse is, like a value for my hypotenuse, I could solve to get the side lengths just by dividing by the square root of 2, and it just goes very quickly. Now, the 30, 60, 90 refers to something with a short leg and a long leg. Okay? So the short leg is opposite to the 30, and we call that x. The hypotenuse is twice the length of that x. And then the long leg is x times the square root of 3. Alright, so knowing these ratios, which you can get from the Pythagorean theorem if you really want to, we can solve for any special triangle. Okay, so here we go. So for part A, they have a triangle called MNO. So I'm just going to draw it out. Now MNO is special because it's a 45, 45, 90. And so they're saying that OM is a length of 2. And so we would need to find the other ratios. They're also calling angle N our theta. Okay? So that's all the known stuff. So I'm going to use red in order to put the stuff that we don't, that we had to solve for. Okay? So remember, with the 45, 45, 90, okay, these two sides are the same length, right? So since OM is 2, ON is also 2. And then if these 2's are counting as my x values, then my hypotenuse would just be 2 root 2. I could get that hypotenuse by using the Pythagorean theorem if I wanted to, okay? You do you. I mean, whatever makes your life easier. And so now relative to that angle, I'm going to go ahead and label our triangle. So across from N, so line OM, that's our opposite. That means this other 2 is our adjacent, and 2 root 2 is our hypotenuse. So now we could set up our trig ratios and solve for them. So the sine of theta, or the sine of angle n, is equal to my opposite over my hypotenuse. Okay, remembering SOHCAHTOA here. So the sine is the opposite over the hypotenuse. So 2 over 2 root 2. Now remember, we do not like having a radical in the bottom. So what I need to do is I need to multiply by the number 1, that's what's going to go in this parentheses, that would cause that radical to cancel out. And so that would be root 2 over root 2. So down here in the bottom, root 2 times root 2 is 2, and that'll cancel out with the 2 in the top. And so my sine is left out as root 2 over 2. Alright, so now my cosine is the adjacent over the hypotenuse. So it's 2 over 2 root 2. Now I don't need to redo that calculation to rationalize the denominator, right? Because I've already done it once. So if you've already done that calculation, you don't have to go hog wild with doing it multiple times. Okay? So now my tangent is going to be my opposite over my adjacent. So 2 over 2. So my tangent is just a 1. So those are my 3 traditional ones. Now I'm going to work on my reciprocal functions. Okay, so the sine goes with the cosecant. Now with this, remember the sine is the opposite over the hypotenuse. I'm just going to put the hypotenuse over the opposite. So I could use my final answer and then flip it. But I find that in this case where we had to rationalize, it's easier to just go back to the triangle and label them. Because here my 2's cancel out and I'm left with root 2. And that's kind of quick. Alright, now my secant goes with my cosine. And my secant would be the hypotenuse over the adjacent, which again gives me root 2. And then my cotangent goes with my tangent. So my tangent's 2 over 2, so my cotangent is 2 over 2. So my cotangent didn't change. So there, it's pretty easy. Not so bad. So now I'm going to do the same thing, but now I'm going to do it with JKL. Okay, I did put a try it on here. Sorry, just making sure I had the common sense to leave room for my try it. So JKL is specifically a 30, 60, 90, where J is the 30, K is the 60, and then L is the 90. Now very specifically, they're telling us that J is our theta, okay? So that's the angle we're referencing. And LK is 4. So if I use my special right triangle ratios to help me get my other sides, we should be good to go. Alright, so the first thing is KL is the short leg because it's opposite the 30. So if I double that short leg, I get my hypotenuse, right? See how the short leg times 2 is the hypotenuse? So that tells me my hypotenuse is 8. And then to get my long leg, I take the short leg and multiply it times the square root of 3. So JL is 4 root 3. Alright, so now that we have that, I'm going to go ahead and label this triangle relative to that 30 degrees. So my 4 is my opposite, 4 root 3 is my adjacent, and 8 is my hypotenuse. And we're set to go through all 6 of those calculations again. So the sine is the opposite over the hypotenuse, which is 4 over 8. So our sine of 30 degrees is 1/2. My cosine is the adjacent over the hypotenuse, so it's 4 root 3 over 8. And so when I do that, I get root 3 over, oops, that's not a 3, Miss C. Root 3 over 2. And then my tangent is the opposite over the adjacent. Now, because that root 3 there is in the denominator, we need to go ahead and rationalize it. Okay, so I'm going to multiply by the value of 1 that cancels that root 3 out. Alright, so you guys could see that the 4's cancel each other out, and I'm left with root 3 over 3 as my tangent. And so now I'm going to do those reciprocal functions. So my cosecant is going to be my sine flipped upside down, so 8 over 4, which is 2. My secant is going to be my hypotenuse over my adjacent, so 8 over 4 root 3. And so we have to rationalize that one, which is like, okay. So I'm multiplying by the number 1 in a way that'll cancel out that radical. So the 8 and the 4 reduce to being a 2. So I have 2 root 3 over root 3 times root 3 is 3. And then my cotangent is just going to be my adjacent over my opposite. So 4 root 3 over 4, which is just root 3. Alrighty, so we're going to do it one more time now just with that try it. Hopefully now it's super easy. So this is another 45, 45, 90. I try to draw it relatively nicely. And so it says the length of the hypotenuse is 5 root 2. And so they're wondering for the sine of theta, where theta is a 45-degree angle. And they're wondering about the secant of theta. Alrighty, so if we're dealing with the sine and the secant, we need our opposite and adjacent in here as well, right? So remember on our last example, the hypotenuse is just x times the square root of 2. So my side lengths are whatever number was being multiplied by root 2. So in this case, because our hypotenuse is 5 root 2, these legs here are each 5. Alright, now if I label this 5 is the opposite, this side is the adjacent. And so actually finding the secant and the sine, they're going to be pretty easy. So our sine, if I use SOHCAHTOA, is the opposite over the hypotenuse. So it's 5 over 5 root 2. Now again, we need to multiply by the number 1 that causes that root 2 to cancel out. And so you could see my 5's cancel out, and I'm left with root 2 over 2 for my sine. Now my secant is the same thing as my cosine flipped upside down. So if my cosine is the opposite over, the adjacent over the hypotenuse, my secant is going to be the hypotenuse over the adjacent. So it's going to be 5 root 2 over 5, good lord. And you can see the 5's cancel out, and I'm left with the root 2. So there we have it, guys. That is how to evaluate trigonometric ratios in special triangles. Until next time.